So it's my honor to chair this session, which is the powerful session of the day. We have amazing speakers, and you will see them go on this stage one by one. Our first speaker is Rana, and I'm going to be a little bit less traditional. I hate reading the title and the author names because probably Rana prepared and she's going to read them anyway, so instead of repeating twice, I'll just share with you one anecdote I heard about Rana, about this paper. So Rana posted it on GitHub and it got 700 likes, stars, right? So it was on the top list of the most liked work or most used work in something. But yeah, we weren't sure how to frame it. So anyways, it's an awesome work and we're excited to have Rana tell us about it.
Thank you for the introduction. So my name is Rana. I'm a PhD student here at Tel Aviv University. Can you hear me? Oh. Can you hear me now? Yes? Okay. This was a work which we presented at this past SIGGRAPH, and I'll also be discussing at the end of the talk some follow-up works. Convolutional neural networks work really well on images for tasks like classification and segmentation. Convolutional layers exploit local spatial correlations, and the pooling layers reduce and strengthen the learned representation. These operators are trivial to apply in images since they are densely and uniformly sampled on a grid. However, extending these operators to the irregular domain is not a trivial task. In 3D deep learning, we also want to learn to classify and segment 3D shapes. However, 3D shapes are inherently irregular. So the first works pioneered this idea of 3D deep learning by converting the shape to a regular representation. For example, by projecting the shapes down to 2D images or a 3D voxel grid, they can use regular standard CNN tools. More recently, there's been a wave of works which have developed irregular CNNs to work directly on the point cloud representation. Point clouds are a list of XYZ coordinates in space, and they are unordered and irregular, so there is no universal convention for applying convolution. However, there have been many works which have had great success applying convolutional neural networks on this type of data, directly on this type of data. In the world of 3D and the world of computer graphics, the most popular representation for 3D shapes is the polygonal mesh. There are not that many works on irregular shapes. There are, relatively speaking, in Israel, there are a good amount of groups that are working on, develop some works which do CNNs on irregular manifolds. In this work, we want to focus on building a CNN which will work directly on the triangular mesh representation and exploit its unique properties. Okay, so what is a mesh? It's an unordered list of XYZ coordinates in space, and also a list of triangles, which are the three indices, the three vertex indices, which define the triangle. So both of these lists are unordered. So the mesh representation has many advantages compared to, for example, the point cloud representation. The first is that it's adaptive and efficient. So we can represent, for example, here the large flat surface is represented with only 2 triangles. However, in more detailed regions, we can use a larger number of triangles to more faithfully portray the underlying surface. Second, the mesh also explicitly contains the surface. So we can disambiguate points, for example, on the 2 camel joints that are very close in Euclidean space by their distance on the surface or their geodesic distance. So we want to build a network that will be invariant to this initial ordering of the vertices and faces, but the mesh is irregular, so it's not clear how we can even apply convolution, since each vertex can have a different number of vertex neighbors, and there is no order between the neighboring vertices. So directly convolving kernels associated with vertex features will result in ordering to variance to this ordering. So in this work, we wanted to develop these basic CNN operators, which are convolution and pooling layers, which we can use, which we showed in this paper for tasks like classification and segmentation. And in this talk, I'll show you a couple of follow-ups that are unpublished. So when we think of a mesh, we think about a list of vertices and triangles, but we have an edge. Edges have this nice property in triangular meshes where every single edge is adjacent to exactly 2 triangles. So this, what's called one ring neighborhood of every single edge, is exactly 4 edges. So in this work, edges of the mesh are like pixels in an image. So every single edge has an n-dimensional feature vector associated with it, and we want to learn convolutional kernels, which are applied on each edge's n-dimensional feature vector and the 4 neighboring n-dimensional feature vectors of each of the neighboring edges. What's the problem? The problem is that given different orderings of the list of edges, we can get a different spatial configuration. So how can we consistently match the edge neighbors to the convolutional kernels in a consistent manner? So this property is called equivariance. So each face in the triangle mesh has a direction, has a face normal, and that defines a consistent ordering within each face. However, there's an ambiguity between, for this particular edge, which face we start with. So the ambiguous pairs are marked in red and blue. So our solution is to apply the convolutional kernel on a simple symmetric feature, which in our case is the element-wise addition of all of the features in the edge A and the edge C. And we apply the convolution on that symmetric feature, as well as the absolute value of the difference between A and C. And the same thing goes for the other pair. So in images, every single pixel starts out with a simple basic RGB vector, which carries little semantic meaning, and then as it goes through the network, it becomes abstracted to a higher dimensional feature vector. In the same way, we also want to define some very simple feature vector, which will also be abstracted. So we chose a 5-dimensional feature vector, which is the angles marked in blue, and the ratio of the height to the base of each of the 2 triangles. So a nice property about these simple geometric features is that they're invariant to similarity transformations. So uniform scale, rotation, and translation will result in the same 5-dimensional feature vector. So the inspiration for our pooling operator comes from a classic technique in computer graphics called mesh simplification. In mesh simplification, we want to delete or collapse edges, where the criteria for collapsing an edge leads to a minimal geometric distortion in the underlying shape. In this work, we want the network to learn which edges to collapse. So this results in a task-driven edge collapse, which is related to the loss function. So an interesting byproduct of that is that we can see visually which parts of the shape the network determined were important for the task, or not important for the task. Okay, so we have this list of edges. Every single edge has an n-dimensional feature vector associated with it. Now we take the L2 norm of each edge feature vector, and we delete edges with the minimum norm. So these are the least active edges, and the number of edges that we collapse in a single pooling layer is a hyperparameter of the pooling layer and of the network. So each deletion of an edge has two main operations. The first is if we want to, for example, if we want to delete this edge, the three edges A, B, and E are aggregated into a single edge P, and we element-wise average those features. In addition, the same thing happens in the bottom face. And then we also need to update the mesh data structures. So the adjacency information, when we go to do the next convolutions, we need to have the correct one-ring neighbors. So this is a dynamic operation that happens inside the network. Then we have this sort of semi-trivial extension of mesh pooling is mesh unpooling. With mesh unpooling, it's also not a learned layer. We just remember which edges we collapsed, and then we exactly restore the same mesh connectivity as before the collapses. And the features that we put in their place are just a weighted average of the pooled features. So to summarize, we have a mesh with a list of edges. We extract for every single edge this 5-dimensional similarity invariant geometric feature vector. Then for every single edge, we extract the 4 one-ring neighbors. We build symmetric features based on the direction of the face normal. And then we apply a convolutional kernel on those symmetric features. And then we have ReLU batch normalization, and then a pooling layer, which will delete edges which are the least active from the learned feature vectors. And then that process continues over and over. We have more convolution, ReLU, batch norm, pooling. Oh, sorry, one last thing I forgot to mention is that the mesh pooling layer has a target number of edges, so we can give the network meshes with different resolution, and it will iteratively collapse each of the meshes until it reaches that target resolution. We can also handle meshes with boundaries, so not watertight meshes, by just padding the convolutions with zeros. Okay, so an aspect that I really like about this work is the property of the mesh pooling operator. So if we have a set of vases and we train one MeshCNN network to classify whether vases have handles and another to classify whether it has a neck, the intermediate mesh simplifications will look different because we train the network to focus on different parts of the shape. And so this idea of sort of a network interpretability is interesting because we can kind of see what happens underneath the hood in networks. Okay, so in the paper we show tasks of classification. So classification, we have convolution pooling layers, and then we need to have a single global vector which will represent the entire shape. So we do a global max or global average pooling, and then we have fully connected layers. And for the task of segmentation, we have an edge-based classifier. For each edge, we predict what the probability is that that edge belongs to a particular class. And since it's a fully convolutional task, there is no fully connected layer. There is unpooling layers to restore the original mesh resolution. So one of the data sets that we showed our results on is a data set that we built to sort of highlight the power, I guess, of working directly on the mesh representation when you have the mesh representation. So we took cubes and icons from 23 different classes. We ingrained the icons into the cube in a very shallow way. And then we trained the classifier to tell us from which class each of the cubes belonged from. So we also sampled the cube with points and trained a point net classifier, and we also trained a spherical network, which maps the cube to a sphere and applies a spherical convolution on the cube. So in the representation conversion, maybe some information was lost. So these are the intermediate mesh simplifications. So you can see that the network mostly collapses edges behind the icons. So this is a human segmentation benchmark where we trained the network to classify for each edge which of the 8 parts of the human did this edge belong to. So because we're working on edges, we evaluated our accuracy based on edges. The point-based approaches test their accuracy based on points, and the face approaches test their accuracy on faces. So the comparison is a little apples to oranges, but you get the idea. But I think what's more interesting than this table is that we published our code online, and our pre-trained weights, and some researchers reached out to us and told us that they used our pre-trained models on real human scan data, and it works quite well. So that's very exciting for us. Our network is invariant to rotation, translation, and uniform scale by construct. But by construct, we're not invariant to different triangulations of the same or different meshings of the same underlying object. So in order to become robust to the different meshings, we rely on data augmentation. So we observed in practice that a relatively simple policy for creating new meshings of the same object resulted in a fairly robust network. So I want to talk about a couple of follow-up works that we are working on right now. The first is a framework where we're using MeshCNN to convert a point cloud to a mesh. So the way we're doing that is we're training a MeshCNN network to overfit the edge-based convolutional kernels to a single point cloud. We take some initial mesh and we deform it such that it will sort of shrink wrap onto the input point cloud. And this doesn't require pre-training or any training data. And the reason that this is kind of interesting is when we compare that to sort of classic techniques, a classic technique for mesh reconstruction from points is Poisson surface reconstruction. And the Poisson surface reconstruction builds into it some type of smoothness prior, and that prior will fill the hole in a way that for us is not the correct underlying surface. However, when we're training a single network to overfit to a shape, it sort of inherently exposes and leverages the repetition and self-similarity present within a single shape. So that's one thing we're working on. Another thing we're working on is using MeshCNN to generate or synthesize new meshes. And one application of that work is if we take this spiky ball over here on the left, the geometric texture that it has, we can use that and project it onto like another shape that doesn't have that geometric texture, and it will add the geometric texture. So in summary, we presented a network that works on triangular meshes. We have this sort of 2 core convolution and pooling operators that in the paper we showed can work for tasks like classification, segmentation, and now I'm showing you that we can use it for even more tasks in 3D. Yeah, we're also considering maybe taking it to graphs or images. So thank you for listening. Please feel free to check out the code online or ask me questions through email or here.
told you, it's a beautiful work. Do we have questions? Okay. The guys with the lighting, it's impossible to see if there are questions when it's dark. No, he doesn't get me. I think there's a question over there. Maybe you can shout or... Oh wait, the speaker is coming to you.
Hello, and thank you for the great presentation. Regarding, in the end of the lecture, you remind some future work about 3D reconstruction. Could you comment maybe on the relation between this direction to, for example, AtlasNet? Okay.
Like the deep geometric prior work?
The first future direction, I think. Basically, you take an initial mesh and you deform it onto the point cloud. So I think, if I'm not mistaken, maybe it has some similarity to AtlasNet, or maybe.
So there was a work which followed up on AtlasNet called Deep Geometric Prior, which used AtlasNet to do something like this. The main difference is that AtlasNet is working on local charts. So each chart that's reconstructed has no information about the entire global shape. So with our work, the convolutional kernels are shared across the entire shape. So this allows us to exploit that self-similarity that's repeating within a single shape, whereas something like AtlasNet, which is looking at small local patches, can only exploit local structures at a very small scale. I don't know if that answers your question.
Let's thank the speaker again.